In this lesson, we are going to learn about chemical equilibrium. Now, what is chemical equilibrium? It is a point in which the chemical reaction will have the following characteristic. First of all, we're talking about the rate of forward reaction versus the rate of reverse reaction. So I have hydrogen and oxygen combined together to make water. Before, we would have a forward reaction, but at equilibrium, or in most reaction, you would also have the reverse reaction. So we have a double arrow that go in both directions. So in this case, at equilibrium, it is a point in which the rate of forward reaction is also, forward, is also equal to the rate of reverse reaction. But how does equilibrium achieve in the first place? In this case, we try to explain with this two graphs. The first one we're going to talk about is the amount of reactant and product. That means we're talking about the concentration of it. So this could be in terms of concentration, and it is compared relative to time as time increase. So first of all, when we have a reaction, of course we are going to have a lot of reactant over here. We're going to have a lot of reactant, and we have almost no product at all at the beginning of time. But over time, this reactant will combine to form the product. That's why you slowly see the product continue to increase, because all this reactant right here will produce the product. And you can also see that the reactant get used up to make the product. That's why it is getting smaller. See how the value decrease over time. Versus the product, because your reactant is being used up to make the product, of course the number of product would increase over time. This will continue until you produce a lot of product. Those products will eventually go through the reverse reaction and make more reactant. Now this will happen over time until that you will see the amount of the reactant and the amount of the products stay the same, and they stop to change over time. So it doesn't matter how much time we increase, the graph will stay like this forever because they are at equilibrium. Now let's look at a different graph. In this case, we are comparing in terms of the rate, not the amount. Two different things, okay? We know that at equilibrium, the rate of forward and the rate of reverse are equals. And of course, this part right here, this is the initial of equilibrium. This is where the equilibrium occurs for this reaction. But let's go back and look at the rate of reaction. Let's go back and look at this graph. First of all, we have the forward reaction. That means reacting or forming to make a product. So we have forward reaction. Then we have the reverse reaction, which is the products are broken down to make the reactant. So it makes sense that at the beginning we have almost no product at all. So of course we're not going to have a lot of reverse reaction. So the rate of reverse reaction is extremely low, where the forward reaction is going to be a lot, because you're going to have a bunch of reactant right here, and they're going to collide and combine together to make the product, just as you see over here. Eventually, over time, the forward rate of reaction will slow down or decrease because all those reactant has been used up to make the product. But on the reverse reaction, now over time you have a bunch of product that's being produced. Those products are going to collide and they're going to break down. They are going to go through the reverse reaction to make the reactant again. Eventually, both forward reaction and reverse reaction are the same. Notice they have the same line right there. That tells you they are at equilibrium. And if they are remaining at equilibrium, this line will remain like that forever. So one last thing about equilibrium is that the amount and the concentration of reactant and product stop to change. And this statement is characterized by this graph. The first statement, the rate of forward and the rate of reverse reaction are equals, are characterized by this graph. So both graphs describe how a reaction achieves equilibrium. When it comes to equilibrium, there is a new constant called equilibrium constant, and is represented by K. So if we first mentioned about equilibrium already, it is the rate of forward and the rate of reverse are equal. The equilibrium constant relate the concentration. Notice we relate the concentration, which is measured in molarity. of the product and reactant. And this equilibrium is happening at a specific temperature. So if you are changing the temperature, the equilibrium constant will also change as well. That's one thing you need to keep in mind. Equilibrium happens at a specific temperature. It is temperature sensitive. So if we are given a chemical reaction and it's happened to be at equilibrium, how do we express an equilibrium constant? It is very easy. You are comparing again the product to the reactant. So basically, if you have a reaction like this, and this represents the coefficient right here. So the lowercase letter are the coefficient, and the uppercase are basically the formula or the substance. To write an equilibrium constant, you would just compare or take the product concentration, raise it to the power of its coefficient. For instance, here we have the products right here. Okay, this is the product. And you can see C and D are raised to the power of their specific coefficient. And it is comparing to the reactant concentration raised to the power of its coefficient. As you can see here, the reactant product, the reactant A and B are raised to their respective coefficient. Let's try an example. However, one thing that we need to keep in mind is that pure solid and pure liquid are not placed in the expression. That means if you have a reaction that has substance in solid or liquid, we just ignore. In this example, we have water being broken down into hydrogen ions and hydroxide. And of course it's equilibrium, so we would have a double direction arrow or double arrow. So let's write an equilibrium constant for this reaction. So K at equilibrium is equal to the concentration of the product raised to its coefficient, which in this case doesn't have any, so we assume it's going to be 1, so H plus. Then we have the OH minus, and it doesn't have any coefficient at all. Then we compare it to the reactant, but the reactant is in liquid form, so therefore we can just ignore it. And that is our answer right there, as simple as that. Let's try another problem. So we are going to write an equilibrium constant again, K at equilibrium constant. And of course we always put the product on top. We have potassium chloride, but this is in solid form, so we can just ignore it. Then we have 3 oxygen gas, so we have O2, and the coefficient is 3, so that's being raised to the power 3. So we have O2 to the power 3, and that's it for the product side. Now let's go to the reactant side. We have potassium chlorate over here, but wait a minute, this is also a solid as well, so therefore we can ignore this. So this is our answer.